Right. Up to now we had seen that different kind of errors associated in our PMMC instrument and how to compensate those errors. Right. If you look at these errors like frictional error, frequency, hysteresis, stray magnetic field error and temperature error, right. All these are what errors we discussed, right. Other than these errors, what are the possibility of errors associated in our PMMC? Look at here, permanent magnet, if you look into this instrument, it may lose its field strength, okay, after some time, okay, that you can call it as even aging effect. Got the point? Due to aging effect, permanent magnet may lose its field strength. That also causes what error in our reading. Okay. So what we say at this moment here, if suppose magnet is losing its field strength, we should take it out and again magnetize the what particular magnet. Okay, means we take a coil and we wound the what across the magnet and we give some external excitation, so that again we can have the what its strength. Okay, we can do that magnetization for our permanent magnet. And one more thing, if you look at the springs, okay, we have two springs, one is in top, other one is in what bottom, right, control springs, right or not. Control springs purpose is to produce the controlling torque as well as what, to lead the current through the operating coil, right or not. So these springs also may lose their stiffness after some usage. Okay. So if they lose stiffness, automatically we have to replace with another new spring, okay, right or not. Got the point? Because of these reasons only, what we say, permanent magnet moving coil instrument, that is PMMC instrument, is accurate one only, but it becomes what, expensive. It is accurate and reliable, but expensive because of these reasons, because regular maintenance is associated. You have to check the stiffness, right. Even we have to check the what field strength of permanent magnet. So automatically some maintenance is involved, then definitely it becomes what, expensive, right or not. But it is the best device to detect the what, DC quantities. So PMMC is the only device to get the what, accurate DC quantities. Only disadvantages are what, you can say, it is expensive when compared with moving iron type instrument, and again some maintenance is associated here, and we cannot measure the what, AC quantities when we compare with what, moving iron type instrument. Only these are the disadvantages. Now we move on to the next session, that is what, applications of PMMC. Just before we mentioned that PMMC is the what, best device in detection of the what, DC quantity. So wherever DC detection is there, we use the what, we use PMMC instrument. Understood? So wherever DC detection is there, we go for the what, PMMC instrument. There only we will be having what, applications of PMMC. So we will be using generally at output side of our like what we can say, rectifier type instruments. Okay, got the point? These are electronic kind of instruments only, but output of rectifier is DC quantity. So at DC detection we will be using what, PMMC instrument. Okay, got the point? Rectifier output is a DC quantity, so to detect that we will be using PMMC instrument. So we are naming it as what, application of PMMC. Here we will first deal with what half wave rectifier type instruments, half wave rectifier type instrument. Okay, half wave rectifier type instrument. Understood? Now, first, how to get half wave rectification here? Simply we use one diode here, right or not? Suppose if I am following with standard sinusoidal signal, which we are giving it to our quantity, that is for our circuit, like this, right? So it is continuous like this. Anyway, Vm, this is minus Vm. So this is our supply voltage V, right? So which we are giving it to our circuit. So only one diode is enough. Okay. Output of this rectifier type is what? DC. So for DC detection we are using what? PMMC. So I am using the circuit form of what? PMMC, like IM or IFS I can say. Got the point? So here it is what? Supply voltage V, that is generally RMS quantity we take. Look into this observation, like diode, if it is having what? Some internal resistance RD I am considering, right? Look into this. This is what DC quantity, or you can say it is what? Average current. Got the point? IM, it is unidirectional one. How to get that current we will see, but before that, what is the output of half wave rectifier? Like this we get, right or not? Here somewhere, so we take like this. This is Vm, this is V out, output, right or not? 0, pi, 2 pi, like this. So half wave rectifier output means it is present only in half cycle. So what is the average output? V out is nothing but what? It is Vm by pi, right or not? For half wave rectifier output voltage is what? Vm by pi only. But I just want to express in terms of our supply voltage, that is RMS voltage V. We know that what is the standard relation for this? V RMS, which is equal to Vm by root 2, right or not? So how to express Vm in terms of supply voltage, that is in terms of RMS? Root 2 into V when we write, that is our Vm. So what I can replace here? What I can replace? So output voltage or average voltage you can say, V average also we can call, which is equal to, replace Vm by with this, we will get root 2 V by pi. Keep it aside. Our intention is to write current expression. So current is flowing like IDC or average current. Got the point? But at the same time, when we extend the range of this meter by adding what? Multiplier resistance or series resistance, we are saying that it is what? Series resistance I am adding like this. Now if I write expression for what? Current Im, what is the current Im or I average, which is equal to V output by total resistance is how much? series resistance is there, meter resistance and diode forward bias resistance is there. This is what our current Im when I write KVL. So, we will get series resistance plus diode resistance plus meter resistance Rm. Now, our intention is to write expression for multiplier resistance. So, if I write for that, what will be the relation here? What is the relation if I write for total resistance? I am taking total resistance other side, RSC plus RD plus Rm, which is equal to V out by Im we will get. First of all, what is V out? I can replace with what? Root 2 V by pi. V is what RMS there. So, root 2 V by pi into Im. So, if you further simplify this, root 2 by pi we can replace with what? 0.45. 0.45 into RMS voltage by Im. This is what our total resistance. We already know that reciprocal of full scale deflection is what? That is our sensitivity, it is DC current. So, DC sensitivity I am writing it as what? 1 by Im. So, when I replace with that DC sensitivity, what we get? 0.45 into DC sensitivity into RMS. Okay, 1 by Im replaced with this. So, now what is another important observation here? In half wave rectifier, so this I can even replace with what? AC sensitivity. So, AC sensitivity in half wave rectifier is what? 0.45 times of DC sensitivity. Right, another important relation we need to memorize. So, how you can write expression for multiplier resistance? Multiplier resistance expression I am writing. Multiplier resistance, that is for RSC. What I can write from this? RSC, which is equal to AC sensitivity into RMS. If I take RD Rm other side, we will get minus RD minus Rm. Suppose if you express AC sensitivity in terms of DC sensitivity, we will get it as what? 0.45 into DC sensitivity into RMS minus RD minus Rm. Okay. This is the expression for what? Multiplier resistance or series resistance, which is connected to extend the range. So, here in half wave rectifier type instrument, AC sensitivity is simply only 45%, you can say, or 0.45 times also you can say. So, this is the way we are extending the range by having multiplier resistance. These are the important relations we have to observe from this instrument. Means when we take up the numericals, you will understand clearly how these are helpful. Okay. So, this is the information related to half wave rectifier type instrument. Next we will see full wave rectifier type instrument. So, there will be change in our circuit, expressions, everything. Okay. Now, after this we will look into that full wave rectifier type instrument. Okay. Right. When it comes to the full wave rectifier type instrument, look at, we will be dealing with bridge rectifier circuit, right. So, 4 diodes we are considering here. And the output is again DC type here. So, wherever output is there, for detection purpose we are having the what PMMC meter model, that is RM. It is IM or IFS we are saying, but here supply we are giving at these terminals. This is our supply voltage, right. So, if you give numbering here D1, D2, D3, D4. So, in positive cycle D1 as well as what D4 in on position, in negative cycle D3 and D2 are what in on position, right. So, if you look at that excitation here, like this, Vm minus Vm, this is our supply voltage B, but outcome of a full wave rectifier is what? It is in this manner, right. This is the output of full wave rectifier. Okay. Two diodes are in on position. So, here D1, D4, D2, D3, next D1, D4, like in sequence, these are in on position here. Output, if you take here for full wave rectifier, what will be the result here? 2 Vm by pi. But we know that V is nothing but what? Vm by root 2. From here, what is Vm? Vm is nothing but root 2 into V. So, you can replace with that. So, what will be the output in full wave rectifier output? So, Vm when we replace here 2 root 2 by pi is what? 0.45. So, anyway result will be 2 root 2 V by pi. This is the output. Anyway, to extend the range, okay, here it is IM or DC or average, we are saying the current. To extend the range, when you add the what? Multiplier resistance. Suppose all the diodes are having what? Same internal resistance like RD. Anyway, one time two diodes are in on position. So, when you write expression for the current IM is equal to V out by output voltage by the what? Total resistance, series resistance. At a time two diodes are in on position. So, we are writing 2 RD plus RM, that is meter resistance. Okay, from here when I replace output voltage with this relation 2 root 2 RMS voltage by the what? Pi into RSC plus 2 RD plus RM. Look into this expression. Our interest is to write expression for total resistance RSC plus 2 RD plus RM. Automatically, what will be the result now? What is the result? Right hand side. 2 root 2 by pi is what? 0.45 we got in our half wave rectifier. Now it is full wave, multiply with 2 means we will get 0.9 into RMS voltage by IM. I am taking into denominator here. So, we already defined, okay, DC sensitivity as what? 1 by IM. So, when you replace with that, what will be the relation? We get here 1 by IM is what? DC sensitivity. So, 0.9 into DC sensitivity into RMS voltage. This I am replacing it as what? AC sensitivity. So, in full wave rectifier output, AC sensitivity is what? 90% of DC sensitivity. So now if I am interested in writing expression for multiplier resistance what we get? Multiplier resistance, which is equal to what we get here, and we can write it as AC sensitivity into RMS minus 2 RD minus RM. If I express in terms of DC sensitivity, then this will be the difference. So 0.9 into DC sensitivity into RMS voltage minus 2 RD minus RM. Okay, in this way we can express the what? Multiplier resistance in case of what? Full wave rectifier type instrument. These are the what important relations we should recognize here. Okay. So what is the main observation here? In half wave rectifier type instrument, it is only 45% of DC sensitivity, but in full wave rectifier type it is 90%. Overall, if you compare, so what we say? Okay, generally what will be the sensitivity? Sensitivity in PMMC is 100%, but sensitivity in full wave rectifier type is what? 90%. Sensitivity in half wave rectifier type instrument is what? Only 45%. So in this way also you can say that, because sensitivity DC nothing but that is our PMMC meter only. Got the point? So these are the expressions we should recognize here. Understood? Okay, wherever DC detection is there, we follow with that, right? Understood? Next we will move on to some numericals related to rectifier type instruments. Here we will see one example, right? Calculate the value of multiplier resistance for a 10 volts RMS sinusoidal AC range of the voltmeter shown in figure, right? The forward resistance of the diode is 0 and the reverse resistance is infinite. And if you look at the even circuit also, full scale deflection and the meter resistance is indicated, and here intention is to find the value of multiplier resistance. When you look at the circuit, it is what? Half wave rectifier type instrument. We know the expression for half wave rectifier type instrument. What is that? For multiplier resistance or series resistance, which is equal to AC sensitivity into RMS minus RD minus RM. And this AC sensitivity we can even indicate in the form of DC sensitivity, that is 0.45 into DC sensitivity into RMS minus RD minus RM. Look at here, DC sensitivity that you can identify from this full scale deflection. What is DC sensitivity here? Which is nothing but reciprocal of full scale deflection of the meter. So we will get 1 by 1 milliampere means how much we get? 1000 ohms per volt we get. This is what? DC sensitivity. Okay. And at the same time, diode forward resistance is how much here? 0. So given RD is what? 0 and RM is given as what? 300 ohms. So now substitute all these information given. So 0.45 into DC sensitivity, how much we got? 1000. RMS voltage is also given, that is how much? 10 volts. So multiply with 10. Okay, multiply with 10 minus RD is 0, RM is given 300. Okay, now 0.45. So 450 into 10, like that we get. So 4500 minus 300. So we get 4200 ohms or 4.2 kilo ohms. This is the multiplier resistance required to observe this reading. Okay. So, it is half wave rectifier type kind of instrument, and this is the way we can have the word example. We will take one more example related to even full wave rectifier type instrument. We will have another example, okay, right, related to rectifier type instrument, but here this time they mention full wave rectifier type instrument. Here also they are asking multiplier resistance. Full wave rectifier type means like bridge rectifier you can consider, right. Now we can impose the given data onto this diagram. Okay. Output side PMMC is there. This is RM. Excitation is given like this. How much input voltage? 10 volts RMS sinusoidal, and all diodes are ideal because forward resistance is 0 and reverse resistance is infinite. So, full scale deflection is given here as 1 milliampere and meter resistance is given as 500 ohms. Now, what is the multiplier resistance? Means connect at this position only. So, this resistance is asking. So, we have a relation for multiplier resistance. Before that, in full wave rectifier type instrument, what is the sensitivity? It is 90% of DC sensitivity. Okay, okay, right. Now, if you use the multiplier resistance expression, AC sensitivity into RMS minus 2RD minus RM. So, replace here 90% of DC sensitivity into RMS minus 2RD minus RM, right. So, 0.9 into DC sensitivity is what? Reciprocal of full scale deflection. So, 1 by 1 into 10 power minus 3. What is the supply voltage? 10 volts minus 2 RD is given 0, RM is given 500 ohms. So, here 0.9 into 10 means 9. So, you take 10 power minus 3 numerator. So, 9000 we will get minus 500. So, what will be the result for RS? RS we can write it as 8500 ohms or 8.5 kilo ohms. Like this, if multiplier resistance is given, we can answer in this fashion. Okay, understood? This is the difference. If it is half wave rectifier, it is 45% of DC sensitivity. Full wave rectifier type means 90% of the sensitivity. Understood? So, we will have one more example related to rectifier type instrument. Look at this question here. A rectifier type instrument uses a bridge rectifier and its scale calibrated in terms of RMS values of a sine wave, and it indicates how much here? 2.22 volts when measuring a voltage of triangular wave. Then what will be the error associated with it? What is the meaning of this? Actually, bridge rectifier circuit is designed, but designed for sine wave, but instead of sine wave they given what? Triangular wave. Then how much error is there? First of all, full wave rectifier with sinusoidal, what is the ratio of RMS to average? Tell me, sinusoidal means form factor we get. So, form factor is the ratio of RMS to average. We know for sinusoidal it is form factor is what? 1.11. And how much it is reading? RMS is coming what? VRMS is what? 2.22. How to get average? Average output VRMS by form factor we can take, means 2.22 by 1.11 means average output is what? 2 volts, right or not? But triangular wave Okay. How to get okay, instead of triangular wave is given, okay, instead of sinusoidal waveform, triangular waveform is given. Like this. So, how to get Vm here? So, Vm, that is maximum value, because once you know the maximum value, then you can find the what RMS value, actual value, right or not? So, here for triangular wave, maximum value will be what? That is average is what? Vmax by 2, right or not? For triangular waveform, average is what? Vmax by 2 we will get. So, from here Vmax will be what? 2 into V average is how much? 2. So, it is 4 volts. From here, what is the RMS value of triangular waveform? That is Vmax by root 3. So, 4 by root 3 means we will get around 2.31. This is the RMS true value. Got the point? True value. But what we are measuring here? This is what? Measured value. So, their difference come automatically. If you give sinusoidal quantity, then absolutely there won't be any error. You are designing for sinusoidal waveform, but you are applying the what? Triangular waveform, right or not? This is the relation for RMS average for what? Triangular. Okay. For sinusoidal, what we get? Vrms will be Vm by root 2. V average we know that 2 Vm by pi, because you are considering full wave rectifier output. So, anyway, our intention is to find what is the error associated with it. You are measuring 2.22, but actual value is how much? 2.31. Okay, measured minus true by true into 100. If you simplify further, minus 3.9% we will get. Understood? Scale is designed for sinusoidal waveform, but you are applying the what? Triangular wave. That is the reason behind this percentage error. Okay. So, like this also we can have the what example. Understood? So, it is purely application of the what PMMC meter, means wherever DC detection is there, we will be using this PMMC instrument, right. So, rectifier output is in the form of DC mode. So, we are placing PMMC meter to detect the DC quantity. Clear? So, next stage, like we will be dealing with some numericals, like any miscellaneous content here, okay, right.